Hello, my name is Michael Ramirez, and today expose quantum mechanics and nanostructures. Introduction, introduction and objectives. This presentation explores how fundamental principles of quantum mechanics are used to understand and estimate the behavior of nanostructures. We emphasize emphasis on semiconductors. The study presents serves as a bridge between abstract theory and real-world nanotechnologies by examining the confinement of electrons at the nanoscale. By modeling the energy levels of electrons using quantum wells, we can analyze the physical dimension and behavior of the semiconductor's device. The goal is to provide a clear concept and quantitative understanding of how quantum confinement affects material properties at dimension of use a few nanometers. On the nanoscale, um, fundamental concepts. At the nanoscale, classical physics fails to describe the behavior of electrons and other particles. Ins- Instead, quantum mechanics becomes essential, particularly the concept of wave-particle duality. Nanostructures are systems with at least one dimension in the range of 1 and 100 nanometers. In such systems, the motion of electrons becomes quantized due to spatial confinement. The, the broadest wave length of an electron becomes comparable to the physical dimension of the system, leading to energy quantization. The, this quantum effect from the basic phenomena observed in the quantum wells, quantum dots, and waves. Understanding this effect is crucial in designing modern nanoscale of electronic and photonic devices. I'm sorry guys for my English is so bad in just only one case. Infinite potential well model. The infinite potential well is a fundamental model in the quantum mechanics where particle is confined between two impenetrable walls. It illustrates the concept that energy levels in a confined space are discrete rather than continuous. The energy of ground state is calculated using E equals h squared divided a ml squared for a 10 nanometer wide well. This yields about a value of 57 milli, millielectronvolts. This energy is significant when compared the thermal energy of the room temperature. This K temp equals 0.0.25 electron volts, showing that a quantum effect dominates in nanostructure and must be accounted for in physical model and device design. Infinite potential well I Ben Daniel Duke model. While the infinite well is useful for conceptual understanding, real systems are better modeled by finite potential wells. The Ben Daniel Duke model improves on this by incorporating effective mass variation across semiconductor materials in a heterostructures like gallium arsenide over aluminum 1 minus 1 minus for gallium for arsenide the electron is confined in the narrow gallium arsenide layer and the surrounding aluminum gallium arsenic acts as a barrier. The ground energy is low around 32 millielectrovolts. Due to the finite height of the world, this value is closer to experimental results and demonstrate how more refined models are necessary to accurately predict device behavior. The model of allow continuity of wave function across material interface. Semiconductor quantum wells. The quantum wells are formed by placing a thin layer of narrow bandgap material like gallium arsenic sorry, between two layers of a wider bandgap material such as aluminum, gallium, arsenic. This configuration confines, confines electrons in one direction, typical the six aces, while allowing free movement in the Fs and Hs. This confinement results in discrete energy states that are tunable by adjusting the well's width and barrier height. Quantum wells are central to the operation of many optoelectronic devices. Their ability to confine charged carriers improves the efficiency of the light emission and absorption, making them indispensable in LED, laser diodes, and high-speed transistors. Fabric techniques and mathematical framework. To create quantum wells with precise techniques like molecular beam epitaxy, MDA, NDA are used to dispose atomos layer of semiconductor. This allows a set control over well thickness, crucial for consistent quantum behavior. Theoretically, these systems are described by the Schrödinger equation, modified for position dependence of mass and potential energy boundary of continuity condition at interface between different materials ensure realistic wave functions. These wave functions all fall into heaven or odd characters levels in both transcendental equations, often recorded numerical methods, especially for finite wells where analytic solution fields. Observation and practical application. The energy levels obtained from quantum models directly influence the optical and electronic behavior of nanostructures. For instance, in multiplied quantum wells, the overlap of confined state and chance, like material iteration approving performance in laser and photoeffects because of their precise energy transition. This structure can be engineered for especially wave layers, enabling their use in the quantum cascade laser. Those are solar cells and wavelength specifically sensors. Their tunability makes them a key component in the model nanophotonic system. This observation affirms the quantum confinement in normally theoretically prediction, but a tool of technical advance in the semiconductor industries. Educational relevance and conclusion. This study is not only technically significant but also serves as an educational resource. The use of simple quantum models like the infinite and finite potential worlds provides students with accessible tools to understand the functionality of nanotechnology. By linking theory with numerical tech techniques and fabrication methods, learning can grasp how abstract principles apply to real-world devices. This integrative approach enhances conceptual understanding and encourages further exploration in application and physics. The study illustrates how quantum mechanics underpins many emerging technologies and this conclusion in undergraduate and graduate curricula prepares future scientists and engineers for research innovation in nanoscale science. Thank you for watching. My name is Iglesia Ramis. I am so sorry for my bad English. And I am from Colombia for this problem with my English. So, bye.